In this section, we'll see directional derivatives and gradient. So first, let's see what is the directional derivative. We have partial derivative f sub x, f sub y, so df dx, df dy. Now, so let's see, this is a weather map. It shows temperatures at different locations. Then partial derivative, for example, Tx, the function is T, temperature. Tx, that's the partial derivative of the function with respect to x. It shows the rate of change of temperature with respect to distance if we travel east. X is increasing. Y is a constant, so y remains the same. So from this point, suppose we're traveling east, x is increasing, then it gives the rate of change of temperature. Then Ty means x is fixed, so y is changing. Then suppose we're traveling north, then the rate of change of temperature is given by Ty. But what if we want to know the rate of change of temperature when we travel southeast, for example, or some other directions? So then we will need a type of derivative, which is called directional derivative. So that will help us to find the rate of change of a function of two or more variables in any direction. All right, so let's see how we define a directional derivative. That means both x and y are changing now. So suppose you have a point, that's when x is a, y is b, so then you can get a corresponding z, and it gives a point on the surface. And then if x is increased from a to a plus hu1, u1, u2 is the direction. So we are changing x and y in the direction of the vector u. So that's a unit vector with components u1, u2. So then x is increased from a to a plus hu1. So you got a x right here, and then y is increased from b to b plus hu2. So here is the new point, and then you can get a corresponding z. So that's another point on the surface. Then for the second line, the slope, we can use f of a plus hu1, b plus hu2. So that's the function value at this point, minus the function value at the original point, ab, and then that's delta z. And then over the change of the parameter, h. So that's slope of the second line. And now slope of tangent line. The only thing we need to do is we let the parameter h be approaching 0. So then you can see the 2 points are getting closer and closer and closer. So that's a tangent line. So the definition of a directional derivative is f of a plus hu1, b plus hu2. So we change both x and y at the same time in the direction of a unit vector u. So u is the direction. And then minus f of ab over h. When h is approaching 0, then that gives the instant rate of change at the point ab. So how to use derivative to find directional derivatives? We don't want to use limit to get the directional derivative every time. And we will define a one variable function. We call this one g of s, where s is the parameter. And we define g of s as f of a plus su1, b plus su2. So for example, your s is 0, then that's just the point ab, f of a, b. S is 0. Maybe when s is 1, the point is here, s is 2 is here, s of 3, s of 4, you can change the parameter s to get different points from a, b. So then g of 0, when s is 0, you can see that's just f of a, b. Then we're actually looking for derivative when s is 0. So this is your h value actually. So we want to find at the point AB, what is the directional derivative? So that's g prime of 0 when s is 0. Then g prime of 0, since g is a function of x and y, and both x and y are functions of s. Remember, using chain rule, the derivative, it should be partial derivative of the function with respect to x, and then by chain rule times dx ds, plus the other branch of the tree, that's the partial derivative of the function with respect to y, and then times dy ds. So that's chain rule. And then when s is 0, we can find the directional derivative. So that's fx, which is the partial derivative of x at AB, and then dx ds. So if you change the parameter, then y is a constant. So then x is increased by u1 because x and y are increasing in the direction of u. So by 1 unit, x is increased by u1. Y is increased by u2. So these components are dx ds, dy ds. All right, so directional derivative. We found the formula. That's fx u1 plus fy u2. Or you can use dot product of the two vectors, which is f sub x, f sub y. Those two are the partial derivatives of the function. Dot product u1, u2, where u1, u2, this vector is the direction vector. We are changing the function in the direction of the vector u. So then we use u1, u2. Now let's see an example problem. We will use this formula to get directional derivative for the following function. All right, so let's see what is the directional derivative. Oh, so this is a notation. Directional derivative in the direction of the unit vector u, directional derivative of the function f of xy. If the function is given by this x cubed minus 3xy plus 4y squared, and the u is the unit vector, square root of 3 over 2, 1/2. So what is the directional derivative at the point 1, 2? All right, so let's see. Using the formula, we can get du f at any point, and is defined as f sub x times u1. u1 is square root of 3 over 2. And then plus f sub y times u2. u2 is 1/2. All right, then partial derivative of the function with respect to x. Then keep in mind y is a constant now, so it should be 3x squared. And then y is a constant, so then the derivative is just 3y. And then 4y squared, since that's a constant number, then derivative is 0. Square root of 3 over 2. And now let's see partial derivative with respect to y. Then x is a constant. So I got a minus 3x. So 0 minus 3x, and then plus 8y times 1/2. So that's directional derivative of the function at any point xy. Now you can plug in x is 1, y is 2. So at the point 1, 2, that means x is 1, y is 2. So let me plug in the number. Then that's, you can do 3 times 1 squared minus 3 times 2, which is 6. And then square root of 3 over 2. Plus negative 3x, that's negative 3, plus 8y, so that's 16, and then times 1/2. Right, so you got a 13 over 2, and then this is minus 3 times square root of 3. You can simplify it to a positive number first, and then minus 3 square root of 3 over 2. All right, so that's how we compute a directional derivative at a given point in the given direction. So you can see in the formula, we have f(x), f(y). So that's partial derivative of the function with respect to x, and also the partial derivative of the function with respect to y. Let me go back to the formula as well. So you can see this is also a vector, and we will define this one as gradient. All right, so this vector is called gradient. We give it a name. It's called a gradient vector. So gradient vector is defined as fx, fy. Right, so it's a vector. Then see, for example, if the function is x squared plus 2xy minus y cubed, then what is a gradient? We use the notation delta f, and we call this one del f, right? Del f, or you can say gradient of f. So then del f is equal to fx, fy. Right? So you can just find the partial derivative of the function with respect to x and also with respect to y. So for this one, with respect to x, the derivative will be 2x plus 2y and then minus 0. And then let's differentiate it with respect to y, then that's 0 plus 2x minus 3y squared. So that's gradient vector. And now, when x is 3, y is 2, you can find del f at 3, 2, by plugging in the numbers. So 2x is 6 plus 4, and then this is 6 minus 3 times 4, which is 12. Okay, so that's 10, negative 6. Right, so that's gradient vector. And what is a gradient vector? What do we know from a gradient vector? So you can see directional derivative means rate of change of the function in the direction of u. And we got the formula, it's del f dot product u, and also dot product has an alternative formula. That's the length of del f times the length of, or the magnitude of u times cosine theta. U is actually a unit vector, which means the length of u is always 1. Cosine theta, the maximum value is 1. And when cosine is 1, then the directional derivative has the maximum value. All right, when cosine is 1, because the maximum value is 1, and the minimum value is negative 1. Cosine is between negative 1 and 1. So 1 is cosine theta 1. That's when theta is 0. So if we are changing the function in the direction of the gradient vector, then the directional derivative can achieve the maximum value. So f has the maximum rate of increase at the point in the direction of the gradient vector. So when u has the same direction as the gradient vector, then the rate of change is maximized. So the maximum rate of change is just the magnitude of the gradient vector. So that's the magnitude of del f. Then when cosine has the minimum value, which is negative 1, that's when theta is when theta is pi. So then we can get the minimum value. So this is the maximum rate of decrease. So the number is decreased in the direction of negative del f. So then the rate of change is in the direction of negative 1 times the magnitude of del f. So then if the directional derivative is 0, then that's when theta is 90 degree. So it's orthogonal. Then cosine theta is 0, then directional derivative is also 0. All right, so when the direction is orthogonal to the gradient, then the directional derivative is just 0. All right, so we can use gradient to get the maximum and minimum rate of change of the function at a given point. Now let's see an example problem. So suppose we have a function that is x times e to the y. So the question is, in what direction does the function have the maximum rate of change at the point 2, 0? And then what is the maximum rate of change? When we say maximum rate of change, we actually means the rate of increase. So then we want the direction to be the same as the gradient vector. All right, so let's see. Let's find the gradient vector first. So del f at any point, that's derivative of the function, partial derivative with respect to x first. So that's e to y. And then now differentiate it with respect to y. So x is a constant, then that's x times e to y power. So this is a gradient vector. Now at the point 2, 0, then the gradient vector is equal to e to the power of 0, y is 0, x is 2. So you got a 2 times e to 0's power. Then that's 1, 2. This is a gradient vector at the point 2, 0. So then the directional derivative has maximum value when we're changing direction in the direction of the vector 1, 2, right? So the function increases fastest in the direction of the gradient vector 1, 2. So f increases fastest in the direction of the gradient vector 1, 2 at the point 2, 0. And the maximum rate of change is the magnitude of the gradient vector at 2, 0. So that's the magnitude of the vector 1, 2, which is square root of 5. So this is the maximum rate of change. If I ask you to find the minimum rate of change, which is the actually the maximum rate of decrease, so then that's when the df, the directional derivative, achieve the minimum value. So that's when it should be negative square root of 5. All right, so the maximum rate of decrease is in the direction of negative gradient vector. So when you are going along the vector -1, -2, then you can get the maximum rate of decrease. So the function value is decreasing. Right? So that's negative square root of 5. And the maximum rate of increase is positive square root of 5. All right, so this is directional derivative. It gives the rate of change of a function in any given direction. And then we also have gradient vector. So we can use that to find the direction where we can get the maximum rate of change of the function.